Good afternoon. I am Mr. Ish. Thank you for joining me. We're looking at some of these odd functions, x cubed, x to the 5, x to the 7. Particularly x to the 5 is the focus over here. You know, with regards to graph, all of these share a particular characteristic. They go to the origin. If you're looking at x cubed, it would be a graph something like this. We're not going to be 100% exact, but let's imagine this right here is a positive 1, this here is a minus 1. As you start increasing that odd exponent, everything starts coming in closer towards these imaginary vertical lines, x equals 1, x equals minus 1, and everything starts to flatten out at the origin. If this is x cubed, x to the 5 might look something like this. Again, remember, it's a bit of exaggeration here. X to the 7 might look something like that. You would have more of a flattening out as the odd exponent increased in dimension, odd dimension, and you would have a flattening here along the origin. Easily, horizontal tangent lines would develop over here, and your point of focus would be the origin 0, 0, because very likely a inflection point would develop. But in all instances, you really wouldn't see local extreme values like a local minimum, local maximum. But let's utilize that x to the 5 and see what it represents with regards to those functions. F of x is equal to x to the power of 5. That's the focus, and that will help us deduce everything for the other two. F of x with regards to the derivative is 5x to the 4. The second order derivative is 20x cubed. If you take that first order derivative and you equal it to 0, 5x to the 4 equals 0 because you want to determine a critical point, you know x is equal to 0. You put that 0 here in the original and you end up getting a critical point 0, 0. But when you take the same value with this x-axis value and you look at everything here in this, you try to determine a sign, like what's coming out with regards to the sign. You're getting a 0, you're not getting a positive or minus. So we're trying to see, and we're seeing that the relative minimum or relative maximum is not really developing for this specific type of functions. We're not seeing local extreme minima or maxima. We just don't see that. When you look at everything here with regards to what we're talking about using the first order derivative test, we have x to the 5 looking something like this, and you start looking at tangent lines. You know you're going to have a 0 over here, then you'll have a plus here. You see the tangent lines would develop something like this. Over here, here's a tangent line, here's a tangent line. But you are reminded here again of the fact that in this side, the tangent lines are above the function. So we might likely be seeing a concavity down. Here, the tangent lines are below the function, so we might be seeing a concavity up. But anyhow, we're not seeing a change over here with regards to the first order derivative from positive to minus, which would indicate a relative or local maximum. You don't see that, nor do you see a change from a minus to a positive, which would help indicate a relative minimum. We're not seeing any of that, so we know that local extremes are not at play with any of these type of functions. However, if you are given an interval such as minus 1 to 1, or what are these intervals would be, they don't have to be symmetric about the origin. It could be minus 5 to 10 or minus 15 to 1. It doesn't matter. But if you were to start plugging these intervals in, at an x-axis using that interval, x-axis equals minus 1, we would end up having a y value. We're looking here an output value of a minus 1, and we would see that minus 1 comma minus 1 represents some sort of an absolute extreme or a global minimum. An absolute minimum or a global minimum. At x-axis equals 1, we would have an output y equals 1, then you know we have 1 comma 1. We'd be looking here at an absolute maximum here, we'd be looking here at an absolute minimum. So for these type of functions, while you don't have the local extremes, the minima and maxima, you can very well have the absolute and the global. Because if you're given the endpoints, which would be your interval start and end, they can develop that absolute extreme value for you. Let's talk about inflection point. You look at this. Where the second order derivative will zero out is exactly where you would have had a transition from a concave down to concave up, or a concave up to concave down. A sign change would have occurred, but here it would be a concave down to concave up. Anyhow, you equal it to 0, x is equal to 0. Therefore, you're looking at a 0, 0. This original critical point ends up being nothing more than a inflection point, and that's exactly what it is, inflection point. When you're looking at these second order derivatives based on the x-axis values, if you're seeing an output which is larger than 0, you're looking here at a concave up, because that would represent a concave up. But if you're looking at x-axis value being placed into your second order derivative and you're having a value less than 0, you're looking here at a concave down. and you remember that to be the case. And you can see it exactly here. If you're taking these minus x-axis values over here and you're putting them right over here, when I'm putting a minus, I retain a minus output, and I'm looking at something here which is a concave down. When I start looking at this positive x-axis values from 0 onward, and I put them here in my second order, remember we're looking at second order, you have positive outputs, and then you know you're looking here at a concave up, and you see that. So remember, this second order derivative with regards to the sign, the placement of the x-axis values can very well help you with concave up, concave down. We have an inflection point, we have concavities. What is our interval of concavities? We have a concave down here from minus infinity coming up to your x-axis value of your inflection point, your 0. For concave up, we have from that same 0 of your inflection point going up to infinity. From here to here, we have a concave up. From here down here, we have a concave down. And right in between, you have an inflection point. This is one of those cases with regards to x cubed, x to the 5, and x to the 7, where rather than developing a local extreme minimum or maximum, you're coming up over here on your curve will cross over its horizontal tangent and it'll go upwards. Hence, you're seeing this positive, positive, 0, positive, positive. You don't see that shift down over here to develop a local extreme, nor do you see something like this to develop either a local minimum or a maximum. You don't see that. In this instance right here, you'd have a local maximum. Here you'd have a local minimum, but you don't see that because what happens is for these type of functions, your curve crosses over its horizontal tangent and it goes upwards, and you lose that ability to generate that local extreme value. But you do retain from the endpoints the ability to have an absolute extreme value, your absolute maximum, your absolute minimum. As a recap, remember x cubed, x to the 5, x to the 7 have a critical point which ends up being an inflection point. Around that inflection point, you have a concavity down and a concavity up. The intervals are here. You don't have any local extreme values, but you can have, if given an interval, you can have global extreme values. And there's not much else to be said about these. There's a specific characteristic to these type of functions, and you're seeing x cubed, x5, x to the 7. They generally share the same attributes. And that's all I wanted to present in this video. Thank you for watching. Have a nice day.